Hello again, this is Math 2231, Alternative Delivery for April 9th, and we're beginning Chapter 5 in your textbook. Please pause, rewind, and play as you go through this video to ensure that your learning is. And again, I want to thank you. There is magic in fighting battles beyond endurance, and I think COVID-19 is a challenge for all of us. But teaching and learning is possible. Grades can be earned and rendered and will be earned and rendered, and your educational goals need not be deferred. So I'm asking you to make some of your magic today. Stay the course and let's get this done. I often do a story at this stage of the course, and so I will tell you the story. Once upon a time, I was a young man starting work at Bell Laboratories after teaching at Purdue for a while, and I wanted people to like me, and I found out that what they did, the young people, played video games. But there weren't video games like you have now. These were text-based games, and in fact the people at the Bell Labs facility wrote their own games. So I found out one of the game masters, he gave me the link to the game, and I started playing. Now this was a game where I was in an enchanted forest and I had a knapsack. I was walking along and the text would tell me, oh, you encountered a sword lying in the road. And I said, well, I might need a sword, so I put the sword in my backpack. And then I walked along for a while and I found a spear, and I say, oh, maybe I will need a spear, so I put it there. I happened upon a bush, and there was a bird in the bush, but there were also berries on the bush, and there was also wood underneath. I said, oh, I might need to make a fire, so I gathered up some of the wood, and I ate some of the berries, and I put the remainder of the berries in my knapsack and continued on. Well, I made progress through the game, but I found out that there was a point where I could not get beyond. And what I would happen is I encountered a dragon, and I tried to have the dragon fetch the piece of firewood, so I threw it to see if the dragon would get on my way. That didn't work. I tried to fight the dragon with my spear, and he fried me once again. Every time he just burned me up, and I had to go back to the start again. I tried chucking the spear at the dragon, and nothing worked. Finally, I asked the game master, I said, gee, I'm having really trouble with this dragon. What's the deal? And the dragon said, or no, well, the dragon didn't talk. Dragons don't talk, but the game master said, um, the bird. I said, what do you mean, the bird? He says, you know that bird you found? Pick it up and put it in your knapsack. I said, well, why would I want to do that? And he said, throw the bird at the dragon. Next time I went through, what I did is I threw the bird at the dragon went poof, and I advanced in the game. That still doesn't make any sense to me, but that's the way the game master programmed the game. Well, the point of this story was not to waste time. The bird is like the antiderivative. You might think, hey, we discussed that concept at the end of chapter 4, section 4.8, and now we're just leaving it alone and we're running off and doing something else. Don't forget about the antiderivative. It's like the bird. It will save you sometime soon. Okay, another element of transition is the key takeaway from the critical thinking project. By the way, I'm still missing some grades. That was to be a self-graded and self-reported thing, so please care for that. The important takeaway, though, from a content point of view is that areas are important concepts in physics and engineering. So today we're going to study area. And so let's begin by talking about a function y equals f of x. And this function is defined on the interval 0, 2, and we want to determine this area. Now, you see we can't use our conventional area formulas because this is a curved surface. That makes the problem much harder. So what we're going to do is we're going to begin talking about, well, how would we go about finding this, this area? So we're going to approximate this area. And I'll estimate the area by dividing up the interval in to n subintervals, each of width b minus a over n. That means they're all of equal length, b minus a over n, and we're going to call that delta x to represent the change in x. Then in each interval, we can form a rectangle whose height is given by the function value at specific points in the interval. We can then find the area of each of these rectangles, add them up, and this will at least be an estimate of the area. Now, a picture is always worth 1,000 words, and so here is a picture. So in here, what we're doing is we're dividing it into 4 pieces. So 2 minus 0 divided by 4 is 1/2. That means each of these subintervals will be 1/2 in length. And in this one, we're going to take the rightmost point to be the value that we're going to take. So we're going to be looking at this rectangle, and we're going to be looking at this rectangle, we're going to be looking at this rectangle, and lastly this rectangle. We're going to calculate those areas. Now, you do have to calculate those areas. Let's do it. And what we find is that the area using the right endpoint gives us an upper estimate of the area, and if we do all of this calculation, this will be for each rectangle. This is going to be the base times the height, base times the height, so on and so forth. I get 5.75, and just looking at the picture, you can say yes, that's an upper estimate of the area. Or we could take the left endpoint as our point of estimate as for the height. Again, we're using 1/2 all the way across there, and so we'll have this rectangle, this rectangle, this rectangle, and the last rectangle here. So the area, if we use the left endpoint, is base times the height. In each case, and at 3.75. In this case, it is a lower estimate of the area. Or we could say, let's take the midpoint of each interval. So the midpoint here would be 0.25. The midpoint here would be 0.75, and so on and so forth. And we can look at this. Now you might say, oh, that's the exact area, but you see it's not, because these are curved surfaces. And so what you have above doesn't equal necessarily what you have below. They don't cancel out exactly, but still it's an approximation. And in this case, using the midpoint, it would be the base times the height for each of those midpoints. And what I will get is 4.65. That is 4 5/8. So now we've got 3 estimates, and this one was actually close to the exact area. And very soon we will learn how to calculate this exact area using calculus. But this is the exact area, and you can see that we have 3 estimates that bounded above and below and give me something in between. Now you want to be careful not to draw any conclusions about how choosing each of the points will affect our estimation. In this case, we are working with an increasing function, so choosing the right endpoints will overestimate and choosing left endpoints will underestimate. If we were working with a decreasing function, it would be the other way about. If we have a function that both increased and decreased on the interval, in all likelihood, we would not be even to be able to determine if we had an overestimate or an underestimate. So the easiest way to get a better approximation is to take more rectangles, increase n. Let's double the number of rectangles used. We were using 4 before, this time we'll use 8. And here are the graphs and the calculations. It is actually useful for students to go through and do these calculations, but this is what we get. And when you look at what we have, you see that I get a tighter upper bound, a tighter lower bound, and this estimate is also in between the two. So increasing n increases the accuracy of these estimates, and I hope some people can smell that a limit as n goes to infinity is coming along. But before you do that, what I would like for you to do is this example 1. I want you to take this function and estimate the area between that function and the x-axis on the interval 0, 4 using 5 subintervals, and for all 3 cases above for the heights of each rectangle. I know there's huge temptation just to skip doing this, but I encourage you to give it a go just to really understand the concept. So I'm going to say press pause now, do the work, and then when you get stumped, or if you don't get stumped, come back, hit play, and we will go from there. So pause now. Let's see how you did. Okay, so the graph looks like this. By the way, you might have had to use some of your calculus tools from chapter 4 to do a good job of graphing that. So the graph is positive, and the width of each of the subintervals, because we're doing them of equal length, is going to be the length of the interval is 4 minus 0, and we're having 5 as the value for n, so that is 0.8. And so that means the endpoints are going to be these values because I just marked them off, and those are the values that I'm going to get. Okay, now this one increased sometimes, decreased others, and increased other times. And so we'll choose the right endpoint here. We don't know if it'll be under or overestimating because it is hard to tell. But what we will do it is the right endpoint. You get these are the values of the bases, and these are the values of the heights. When you plug those in, you should have gotten 28.96, just under 29. When you look at the left endpoints, you get this. It's pretty clear to me that that's going to be an underestimation, but anyway, the area for the left then that you should have gotten was 0.8. That's going to be the base in every case, and then times the height, then we get 22.56. If you use the midpoint, and you had to do some calculations to find out what the midpoints were, these are the midpoints that you should have gotten. And you take base times height and add up, you get 25.12. For comparison purposes, it is going to be this, which is just a little bit over 25, and so you see it's pretty close to that, except this is going to have 3 infinitely repeating, and so that's actually a little bit of an underestimate. Again, the midpoint did a better job than the other two. Well, this is the case more often than not. It won't always be the case, so don't expect that to always happen. Now we're going to move in steps onto what is a more general case. So let's start out with f of x being bigger than or equal to 0 on a general interval AB, and we'll divide the interval into n subintervals, and we're still at this point in time making these intervals of equal length. Again, we're going to relax that as we go forward too. But for now, delta n is b minus a, the length of the interval divided by n. And here again, I'm saying the intervals don't have to be of equal length, but it's easier to talk about here. We're going to relax that later. So the endpoints of each subinterval, then we start at A, we add delta x once, we add delta x twice, so on and so forth, and we get this collection of subintervals. Now what we're going to do is we're going to choose a general point, not necessarily the midpoint, the right endpoint, or whatever, a general point in each of those subintervals. So x1 star is from the first subinterval. x2 star is any point in the second interval, and so on and so forth. These points will define the height of a rectangle in each subinterval. Note as well, these points do not have to occur at the same point in each subinterval. We've chosen those points, and I guess I covered all of that. Okay, so then the area is going to be approximately, what I'm going to do is I'm going to take the base. Now right now we're assuming the base is the same. It doesn't have to be, but if it's the same, it's delta x every time. And what we get is that the area is approximately, this is the height. It is the function value evaluated at x1 star, x2 star, xi star, and xn star, and everything in between. Now, if we use, so the area is approximately equal to that. If we were to use summation notation, the area estimate then is, the area is approximately, this is the summation, as I, the index, runs from 1 to n, f of x sub I star, that is the height, times delta x. The summation in the above equation is called a Riemann sum. And so that is an important concept. To get a better estimate, we take n larger and larger. And in fact, if we let n go to infinity, we have an exact area. The area, in other words, is equal to the limit as n goes to infinity of the summation j equals 1 to n. You see the limit is being taken on the top limit of the summation, f of x sub I star times delta x. So you see, calculus is, again, the study of limits. Before leaving this section, though, we have to address one more issue. To this point, we've required the functions to be positive in our work, but many functions aren't positive, and let's in fact look at this function, y equals f of x equal x squared minus 4 on the interval 0, 2. If you look at the graph of that, that's all underneath here because that really is the x squared term shifted down by 4. So all of these f values are negative values because they'll have negative y values. So if we evaluate our and use the midpoints of each of those subintervals, what you get is 1/4 times the, so it's the base times the height, base times the height, and so on and so forth. But the answer is going to be negative because all of the heights are negative. And so if we do that calculation, this is what we had before. If we do that calculation, we get minus 1.34375. So you see the areas showing up negative. So what we find is that the net area is equal to the limit as n goes to infinity of the summation j equal 1. I'm using j as the index here. You can use anything. It's a dummy variable. J equal 1 to n. The limit is being taken on the n that is up here. This is the height, and this is the value in the jth subinterval that we pick x star in the j, x j star. In the interval, we plug that into f, and then I'm actually letting myself be a little more general here because actually we didn't need to even pick those intervals to be the same size, so this actually could be variable as well. That doesn't have to be delta x, it could be delta x sub j. So that is the big finding for now. Okay, so next time, more on summations in our next video because we will be working a little bit with them. Students should read chapter 5.1 in our textbook and especially read the examples because the examples that I do are not the examples that are in your textbook. And I recommend doing homework in a section. As always, I suggest trying to do every other odd problem. That's a nice cross-section of problems. Failing that, and some students just say I don't have time to do that, then I recommend you do every other odd problem, and so on. But you do want to do a cross-section of even and more challenging problems. And you should also do an assessment on Chapter 4. I have posted this in your syllabus tab, and you should complete it before next period. Next period, which I guess is on the 14th, I think, I will provide a key and grading rubric in a YouTube video on the 14th. And it consists of 15 problems from Chapter 4 to be self-graded and self-reported. And you should plan to have this finished by the 14th. You do the grading. I will trust you to do it straight up. I will trust you to grade it fairly relative to partial credit. And please do not send me megapixels of images to unpack and read. Now you might say, wow, I really wish that, that you were grading these. Well, rest assured that the final exam will be different, however, so do stay engaged and be learning the material, because you will be held accountable for there. Now more than ever, time is precious. Each day must count. Do the math. It will make you strong. Take care of yourself.